All right, Algebra 2 students, I appreciate you finding the time to get your notes taken care of. Today we're going to be looking at equations of logarithmic functions. Please copy the title as well as the objective. And our objective for today is to learn to interpret the equations of logarithmic functions. Now you're going to see a lot of similarities to some of the things that we talked about with exponential functions, because as you should know by now, the logarithmic function and the exponential function are inverses of each other, and we should also know by now that logarithms are another way of writing down exponential expressions. Okay, so these are very, very closely related, so a lot of the same stuff we saw before is going to apply today. Okay, the parent logarithmic function undergoes many of the same transformations that other functions we have studied did. Okay, so a lot of the stuff you're going to see here, you're going to recognize. Some of it you will recognize but have to come to a slight adjustment in order to understand it. But here we go. The parent logarithmic function is simply log of base b, I'm sorry, log with a base b of x. Okay. Now, obviously, there's a lot of opportunities for coefficients and constants to pop up inside of this expression. One of them would be a coefficient in front of the logarithm. The base of the logarithm, of course, can change as well. The coefficient in front of x can be changed. And then, of course, we can have constants h and k either being added so that they directly affect x or so that they directly affect y. Okay, so let's take a look at these values and see what each of them does. Okay. Clearly, h is our phase shift. It is inside of the argument of the logarithm, pardon me, and it is causing a horizontal shift. And as always, the sign of h there is supposed to be negative, so if h changes the sign, it would appear positive. And as always, k represents a vertical shift. It will not be part of the argument. It'll be a constant being added or subtracted so that it can affect the overall y value, not the x value. Now the coefficient a is going to compress or stretch the graph vertically, okay, being the coefficient of the entire right side of the problem. Okay, that is in a position to directly affect the y value as a changes, the size of y changes. So we're going to be compressing or stretching the graph vertically by changing the a value. The base can compress or stretch the graph, and this one's kind of tough to verbalize. You're just going to have to see some graphs in order to get a grip on it. Okay, it does compress or stretch the graph, but it's not a very pronounced change. It is altering it, but in very small quantities. So you'll just have to see this one work to understand it. C, of course, changing the coefficient of x, compresses or stretches the graph horizontally. Obviously, changing the coefficient of x changes the x value and is either going to cause it to be in a bigger hurry to get off of the graph or in less of a hurry. Okay. Now, just like with the exponential graphs, I've given you some visual representations of what these graphs are going to look like as some of these values change. Now, for those of you that actually are taking your notes, I need you to do a little bit better job of doing these graphs. Okay, if you do these graphs in such a big hurry that you can't tell the difference between the graphs that are given, then your notes are basically becoming useless. Your notes are not a chore just to get through. They are a tool to help you review and learn and refer back to it. If you can't refer back to them, then you basically have just wasted paper. Okay, so let's take a look at what would happen inside of the logarithmic function if the coefficient a is changed. Now we said that a, adjusting it, would cause the overall y value to be altered. The graph is going to be compressed or stretched vertically. Okay, so there in the center, A is when A is 1, that is the basic kind of reference starting point. This is what A should be doing. Okay, so the 1 in the center is what A would the function should look like when A is 1. When A gets smaller than 1, the graph is in not so big a hurry to get to rise up. And when A is larger than 1 over there on the right, obviously the graph is in a bigger hurry rising up. Because we said changing the A value directly affects the Y value, which is basically your height change. Now, of course, A can be negative values, and as we've seen plenty of times before, when you change the sign of the right side of the problem, all you have done is turned the graph upside down. So once again, if A is a negative value, but still between 1 and 0 on the number line, the graph is not in a very big hurry like the one on the left. When A is negative 1, that is the correct speed as far as the height change. However, it's upside down because of the negative. And then on the right, when A is smaller than 1, meaning it is between -1 and -infinity on the number line, the graph is in a bigger hurry as far as rising to infinity. Okay. Now let's take a look at what happens when the B value is changed. Now, like I said, changing the base of the logarithm, it does affect the numerical value of the equation, but in a lot of cases it's not affecting it in a very profound way. Okay, but there are a couple of things that we want to look at. Okay. We stated in the beginning that the base value for a logarithm is not allowed to equal 1. This is the same as it was with the exponential function back last unit. Okay, so the base value wants to either be between 0 and 1 on the number line, like the graph on the left, or wants to be larger than 1 on the number line, like the graph on the right. And just like with the exponential function, we can see that we have a direction change. Now with the exponential function, that caused the graph to change, from horizontal to the left and vertical to the right to vertical on the left and horizontal to the right. However, remember that the logarithmic function is an inverse of that function, so we're not seeing a change in the graph from left to right. We're seeing a change in the graph from up to down. Okay, so when we are larger than 1, which is typically thought of as the more common parent function, then we're looking at the graph over there on the right. Okay, going to the left, the graph is mostly vertical, and then going to the right, the graph is mostly horizontal. Okay, but when you turn that graph, when you get between 0 and 1, it is still mostly vertical to the left and mostly horizontal to the right, but notice that the vertical aspect is changed. Okay, so the greater than 1, the vertical is more down, and to the right, the vertical is more up. Okay. Now, as far as the negative numbers, you don't need to spend any time worrying about these. Okay, base numbers, remember I told you, is a system of counting. Okay, so we are not going to be looking at any negative counting systems. That would be pretty mind-bending for us. Okay, so we're not going to be looking at B being smaller to 0. Those are actually imaginary values, so they don't exist on our normal graph. Okay. The last constant for us to have a look at would be C. We're not going to take a look at H and K because you should be well familiar with those by now. Okay, so let's look at what happens when you change the coefficient of the X value. Okay, now you can see some changes in these three graphs. It's not as strong of a change as we saw with the coefficient A being altered. But anyway, in the center there, C equals 1. That is kind of the reference point. It's supposed to be a 1 in the parent function, and you can see the graph and its speed. Okay, when the X value, the coefficient of X, gets smaller than 1, like the graph on the left, you can see that the graph is pulled more horizontally. Okay, so it's like the graph is in a bigger hurry to get off the side of the screen. As such, it does not have as much time to rise up. But over on the right side, when the coefficient of X is larger than 1, it is like the graph is allowed more time in the screen in order to rise up. Okay, so this is kind of similarly related to the C value. A and C both kind of behave the same way. When A gets bigger, the graph gets taller. When C gets bigger, the graph gets taller. But those are kind of the same effect, but because from a different cause. And similarly, if A gets smaller than 1, the graph gets kind of pressed down toward the x-axis. And when the same thing is true with C, but again, same effect, different cause. Now the C value can go negative as well, okay, and reversing the value of x obviously just sends the graph the other direction on the x-axis. Okay, so let's take a look at a couple of examples here. These are not difficult. It's kind of the same idea we've been facing all along. Here we have a function y equals log base 8 of x plus 3 plus 1. Okay, now as always, we need a starting point in our graph to figure out where we should go or where we should begin so that we know where to move away from. Now remember that these logarithmic functions want to cross the x-axis at 1, 0. So any adjustments that h and k make are going to adjust from 1, 0. Okay, looking at h, we have x plus 3. It's supposed to say x minus 3, so that means that the 3 must have a negative of its own. So the graph is going to be moved 3 units to the left, and then the k value is positive 1. That's supposed to be a positive, so we are moving up 1. So if we come left 3 units and up 1 unit from 1 comma 0, then we end up at negative 2 comma 1. Okay, so that's a good point to start, so we can enter that right in the center of our chart, and we of course can plot that point. Now, the graphs on these, okay, on our steps, what we really need to be concerned about is the graph been turned around backwards? Is it still vertical on the left side and horizontal on the right side, or has something turned the x value around? Well, the only thing that can turn the x value around is changing the sign of x. And that has not happened in this graph. So when we select points of x, we are going to pick small steps to the left of our starting point and large steps to the right. Now on these, you're going to need to take quarter step units here, quarter of a unit steps on your small side. Before, some of y'all were taking half steps, and that's fine for the exponential function. But on the logarithmic, the asymptote is actually very close to this starting point. And if you take half steps, you're actually going to jump to the other side of the asymptote, and then you're going to get values that no longer compute. Okay, so we're going to take some quarter steps here. So from negative 2, I took a quarter step to the left, negative 2 1/4. Another quarter would be negative 2 1/2, and another quarter is negative 2 3/4. Now going to the right side, the graph is very flat, horizontal, so we're not too worried about it, taking some big steps there on the whole numbers. Okay, so as always, we're going to take these values one at a time, and we're going to plug them in for x, and then we will find out what our y values are. So plugging them in one at a time, we end up with a bunch of crazy decimal points. Okay, but there are all of our ordered pairs. Our ordered pairs turn into points in the graph. As you can see, very tightly packed in there, just to the left of x, but based on your points, you get to connect the dots, and there you go. Okay, one more. Y equals negative 2 log base 2 of x plus 3. Okay. Now on this one, we should expect that our graph be in a bigger hurry because our a coefficient is larger than it should be, and it's also negative. So we should expect our graph to be upside down. So instead of coming up from negative infinity on the y-axis, it's going to drop down from positive infinity on the y-axis. Okay. So again, let's see if we can figure out our starting point. The starting point for all logarithmic graphs is at 1 comma 0, and hk will adjust it from there. This time we have no value of h, so the x-axis will not move, but we do have a k value of positive 3, so it's going to move up. That would put our starting point up at 1 comma 3, so that's a good point right for the middle of our graph, and of course that gives us a plot in the graph. Okay. Again, we need to kind of check and see which direction the graph is moving, which side do we want all of our small steps on, and which side do we want the larger steps on. Again, the only thing that can make the graph turn around is a negative x, and we do not have one. So once again, moving to the left of our starting point, we're going to take very small quarter steps, and then moving to the right, we're not so much worried about the height change, so we'll just go ahead and make it easy on ourselves and take whole number steps. Okay, so there's our quarter numbers moving to the left and our whole numbers moving to the right. As before, we will plug in these values for x one at a time. You will need the help of a calculator to get this math going. We're still not good enough to be able to understand those different log bases. Okay, but get the decimals back out of your calculators, fill in the chart after plugging in your values one at a time. Okay, and there's all your ordered pairs. Your ordered pairs lead to points, and points lead to connecting the dots. And there's our logarithmic graph. We said it was going to be stretched out vertically more than it should have been. That is truly the case, and we said it was going to be upside down, and that is the case also. Okay, so hopefully this is not completely new information to you, just a new function to work with as we continue our discussions of these new parent functions here in Algebra 2. I appreciate you finding time to get your notes taken care of, and I'll see you in class.